Hi everyone, this is Babaiah, Assistant Professor of EC Department, MLR Hyderabad. Today I am going to explain about the expressions of steady state error for the various inputs. In previous class, we learned time domain specifications and also how to derive the time domain specifications. All these are learned from the previous session. But today I am going to explain about expressions of steady state error for various inputs. Like here, see, coming to the overview of today's session, just to derive the expression of steady state error when the unit step input signal. If we are going to apply the any input signal as a unit step, based on that we are going to derive the steady state error and also derive the expression of steady state. This one, expression of steady state error when the unit ramp input signal. Here first one is the unit step input signal and unit ramp input signal, and third derivation or expression of steady state error when the unit parabolic input signal. Right, okay, all these are now we are going to derive, right? So let's move on to the first one. Derive the expression of steady state error when the input is unit step input signal. Unit step input signal, right? Here in steady state error, the basic formula we know already. So steady state error, that is equals to limit s tends to 0 s into r of s divided by 1 plus g of s into h of s. This is the steady state error formula. For that we are going to apply the unit step input. So unit step input in terms of s domain, the r of t in terms of time is r of t equals to 1. So that is equals to, so 1 divided by s. 1 divided by s here, see. So in place of s domain, the r of t is represented in time domain. Now it is converted into the s domain, that is r of s is equals to 1 divided by s. So in place of a r of s, we are going to substitute 1 by s. See here, ESS, that is steady state error, equals to limit s tends to 0 s into r of s is, we know, 1 by s for unit step input. So 1 by s divided by 1 plus g of s into h of s, right? So here s and s both are get cancelled. So 1 divided by 1 plus g of s into h of s. So that is equals to limit s tends to 0. Here s terms are in this form. So 1 plus limit s tends to 0 g of s into h of s. We know this term. So limit s tends to 0 g of s into h of s is nothing but the positional error constant. Positional error constant. The constant kp, or representing it is kp, k suffix p, that is nothing but the positional error constant. So positional error constant kp equals to, we know that. So limit s tends to 0 g of s into h of s. G of s into h of s, right? So here in place of 1 by 1 plus limit s tends to 0 g of s into h of s, you should write the kp. So 1 by 1 plus kp. So here kp is the positional error constant. For type 0 system, the steady state error is here. Type 0 system means, type 0 system is nothing but, what is mean by type already, all these are learned or I already explained in previous sessions also. Typo and order, all this, right? So here kp is nothing but the positional error constant, that is equals to limit s tends to 0 g of s into h of s. Okay, so limit s tends to 0, k is constant into s plus z1, s plus z2, s plus z3, all these are the poles, sorry, zeros, and here denominator part s plus p1, s plus p2, s plus p3 is nothing but the zeros. Here simply g of s, this is the in denominator part, right? So denominator, this is g of s into h of s, denominator part, that is nothing but the poles of the system, right? So poles s into s plus p1, s plus p2, s plus p3. Here there is a no pole present at origin. So there is a no pole present at origin. There is a single s term is not available in the given this positional error constant. So here, so this is the type 0 system because of there is a no pole present at the origin. So that's why we call it as the type 0 system. Here S equals to 0, substitute S equals to 0 here, 0 0 and 0 0, all the place of S is 0, substitute, you will get the K into Z1 Z2 Z3 divided by P1 P2 P3. So this is complete value is nothing but the constant, right? So constant. So steady state error, we know that ESS equals to 1 by 1 plus Kp. So 1 by 1 plus Kp, that is steady state error is equals to what? Constant. Here ESS equals to 1 divided by 1 plus Kp value is constant. So constant 1 divided by 1 plus constant. 1 plus constant is nothing but constant. 1 divided by constant is nothing but constant finally. Okay. So that's why. So steady state error is equals to constant for the type 0 system. For type 0 system, the steady state error is constant. So here see, hence in type 0 systems, when the input is unit step, there will be a constant steady state error. So constant steady state error, right? Next, type 1 system. For example, type 1 system. So here Kp equals to limit s tends to 0, g of s into h of s, positional error constant we know. So limit s tends to 0, k into. Here type 1 system means one pole present at origin. So one pole is this one, present at the origin, s term, on s term here. Okay. This one is the pole present at origin. K into s plus z1, all this numerator part is the zeros and denominator is the poles. So here substitute s equals to 0, all this. So 1 divided by 0. So 1 by 0, that is equals to what? Infinity value. So infinity. So ESS equals to what? 1 divided by 1 plus Kp. Already we know this. So in place of Kp, you should substitute the infinity. 1 by 1 plus infinity. 1 plus infinity is nothing but infinity. 1 by infinity is nothing but the 0. 1 by infinity is nothing but 0. So what is the steady state error for type 1 system? Is 0. Steady state error in this, the type number and above systems, type number 1 and above, type number is 1 2 3 4, all this, you will get the steady state error is 0 only. So for that, no need to calculate the type 2, type 3, type 3, so on, because of type 1 is got the steady state error is 0. Next type 2 also 0 only, type 3 also 0. So that's why type number 1 and above, for unit step input, the value of positional error constant is infinity and steady state error is 0. Positional error constant is infinity and steady state error is 0. These two terms are very important. Next, move on to the next second. Derive the expression of steady state error when the input is unit ramp signal. Input is unit ramp signal. When we know that formula, steady state error is ESS equals to limit s tends to 0, s into r of s divided by 1 plus g of s into h of s. By applying the unit ramp signal, when unit ramp signal in terms of s domain, r of s equals to 1 divided by s square. In place of s, you should substitute 1 by s square. Just substitute s and 1 s get cancelled. So limit s tends to 0, 1 divided by, here one term s is there, so denominator. So denominator, so s into 1, s plus s into g of s into g of s. Okay. Now limit s tends to 0, just to substitute here. Limit s tends to 0 here, s plus 0, that value is 0. Next limit s tends to 0 into s into g of s into h of s. That is nothing but the velocity error constant formula. Okay. Here kv equals to limit s tends to 0, s into g of s into h of s, that is the velocity error constant. Velocity error constant for type 1 0, type 0 system, type 1 systems and type 2 system. What is the steady state error and what is the velocity error? Now we are going to do that one. Just here observe, we know that velocity error constant, limit s tends to 0, s into g of s into h of s, right? So limit s tends to 0, here s is there, s, so g of s into h of s, we know that k into s plus z1, all the zeros and denominator part is all poles, here k into. So substitute s equals to 0, 0 into something is 0, so you will get the kv equals to 0. For that, the steady state error equals to 1 divided by kv, right? So 1 divided by kv, that is nothing but 1 divided by 0 is nothing but infinity. So steady state error is infinity for type 0 system of unit ramp signal. See, observe. Hence, in type 0 system, when the input is unit ramp, the steady state error is infinity. Coming to the type 1 system. Type 1 system is one pole present at the origin. So, one pole present at the origin. We know that velocity error constant, limit s tends to 0, s into g of s into h of s. That is equals to limit s tends to 0. Here s is there. So, g of s into h of s. We know that k into s plus z1, s plus z2, s plus z3 and so on, divided by s. One term s, one is plus one pole present at origin. So, s to s plus 1, s plus 2, s plus 3 and so on, s plus pn up to. Okay. So, here k into, just substitute 0 in place of s, you will get the k. Here s both cancel. So, k into z1 plus z2 plus z3 divided by p1, p2, p3 and so on. So, finally that value is nothing but the constant. So, 1 divided by constant, that is steady state error, equals to 1 divided by kv. So, kv is nothing but value constant. 1 divided by constant is nothing but constant. So, that is nothing but for the type 1 system. Type 1 system for unit ramp, there will be a constant steady state error is occur. Okay. So, type 1 system, the input is unit ramp, there will be a constant steady state error. Steady state error. Constant steady state error. Okay, for type 1 system. Coming to the type 2 system, just observe type 2 system, nothing but the two poles present at the origin. Already we know that velocity constant, limit s tends to 0, g of s into h of s, that is limit s tends to 0, s into k, s plus z1, s plus z2, s plus z3, so on, divided by s square, two poles present at origin. So that's why we call it as type 2 system. So s plus p1, s plus p2, s plus 3 and so on. Substitute s equals to 0, where some one s both when cancel. So 1 divided by s, nothing but the infinity. So kv equals to infinity. So that is steady state error is nothing but 1 divided by kv, right? So 1 divided by infinity, nothing but 0. So steady state error value for the type 2 and above systems. Type 2 and above system for unit ramp input, the steady state error is 0. The velocity error constant is infinity. So type 2 and above, type 2 and above values, above systems, kv is infinity and steady state error is 0. Type 2 and above systems for unit ramp, signal. Unit ramp signal is square, right? So type 2 onwards, steady state error is 0. For example, just simply you can remember like this: unit ramp signal. Ramp signal is nothing but in terms of s domain is 1 by s square, power is 2. So type 2 systems onwards, type 2 and above system, steady state error is going to be 0. Simply you can remember like this. And type 1 systems up to here, unit ramp, unit step is nothing but 1 by s power of 1 only. So type 1 systems and above systems, okay, steady state error is 0, like that. Coming to the third one, derive the expression of steady state error when the input is unit parabolic input signal. Unit parabolic input signal, we know steady state error again. This is the same formula. ESS equals to limit s tends to 0, s into r of s divided by 1 plus g of s into h of s, right? When the input is unit parabolic, that is r of s equals to 1 divided by s cube. Here 3 maximum power, s power of 3 is there. So type 3 up to, we need to calculate the up to type 3 systems. Type 3 and above systems can, as the steady state error is 0. Simply we just, now we are going to see that steady state error is equals to limit s tends to 0, s into r of s, in place of r of s 1 by s cube divided by 1 plus g of s into h of s. Limit s tends to 0, here s 1 s cancel, 1 divided by s square, so s square into 1, s square plus s square into g of s into h of s. Now we know that s square into g of s into h of s, first substitute s equals 0, here 0, Okay, 1 divided by s square g of s into h of s, limit s tends to 0. This term is nothing but the acceleration error constant, or auxiliary error constant, parabolic acceleration error constant, that is the Ka. So we know Ka equals to what? Limit s tends to 0, s square into g of s into h of s, simply parabolic s square into g of s into h of s. Next move. So type 0 system means there is a no pole present at origin. We know already, limit s tends to 0, s square into g of s into h of s. Already we know that g of s into h of s, k into s plus z1, s plus z2, s plus z3 divided by s plus p1, s plus p2, s plus p3. So substitute s equals to 0. Here 0 into something is 0. You will get the 0. So steady state error equals to 1 by ka. So ka equals to 0. So 1 by 0 equals to infinity. Steady state error is infinity for type 0 system. Hence, the type 0 systems for unit parabolic input, the steady state error is infinity. Next, coming to the type 1 systems, Ka equals to, so acceleration error constant Ka equals to limit s tends to 0, s square into g of s into h of s. Already we know that limit s tends to 0, s square g of s into h of s, nothing but k into s plus z1, s plus z2, s plus z3, so on, divided by s into s plus p1, s plus p2, s plus p3, so on, 0. So steady state error is equals to 1 by ka, that is equals to 1 by 0 equals to infinity. 1 by 0 equals to infinity. Hence, in type 1 systems, for unit parabolic input, the steady state error is infinity. Steady state error is infinity. Type 1 system for unit parabolic, steady state error infinity, and type 0 systems for steady state error is infinity only. Next, coming to type 2 systems, 2 poles present at origin, same formula, ka equals to limit s tends to 0, s square into g of s into h of s, s square into k into s plus z1, all the zeros in denominator, all the poles. Substitute s equals to 0, k into z1, z2, z3, p1, p2, p3. Here place of s 0, 0, 0, 0. So z1, z2, z3, p1, p2, p3. Okay. Next, here s square both cancel. So value is constant. So steady state error is equals to 1 by ka, 1 by constant. That is nothing but constant. From that we are going to observe just type 2 system. For type 2 system, when input is unit parabolic signal, there is a constant steady state error will be occur. See here, type 2 system, when the input is unit parabolic signal, there will be a constant steady state error. Type 3 system, Ka equals to means acceleration error constant, that is equals to limit s tends to 0, s square into g of s into h of s. Limit s tends to 0, s square into k into s plus z1, s plus z2, s plus z3, so on, s cube, s plus p1, s plus p2, s plus p3, so equals to s equals to 0. Substitute s square cancel, one s term is there, so 1 divided by 0 nothing but infinity, so 1 by infinity nothing but the 0. So that is steady state error equals to 0, right? In the type number 3 and above systems for unit parabolic input, the value of k, acceleration error constant is infinity. Ka equals to infinity. For the type 3 and above systems, acceleration error constant is infinity, and steady state error is 0. Steady state error is 0, right? So all these are the direct expressions of the steady state errors for different types of systems, right? This is about the derive the expressions of steady state error for the various inputs. Like inputs is unit step and unit parabolic signal, unit ramp signal. All these signals, by applying all these input signals to, you will get the steady state error and acceleration error, or else static error constant. All these static error constant are the acceleration error constant, and also velocity error constant, and velocity, acceleration error constant, positional error constant. All these are nothing but the static error constants. Simply we say that. Okay. This is about the derivation of the or expressions of steady state error for various inputs like unit step input, unit ramp, and parabolic signals. Coming to the next class, we are going to learn the some problems based on the time domain specifications as well as the steady state errors, static errors. Okay, until then, thank you.